to start off, Freddie Otto, please.
Yeah, thank you very much for inviting me. And I think I'll start straight away with wild weather. So this is a picture of the aftermath of the Typhoon Haiyan, which hit you'll probably all remember that, which hit the Philippines last year, exactly at the same time when in Warsaw, the conference of the parties had their climate discussions. And taking this typhoon as an example of climate change, the delegation of the Philippines went into hunger strike and used this specific extreme weather event to push their agenda forward in the discussions at the COP. So this is certainly wild weather. However, whether or not it is climate change is something that we actually don't know at the moment, and which we can't say for this particular extreme event, the Typhoon Haiyan, despite it being adopted also by the UNFCCC Secretariat as one of their examples that they always show for anthropogenic climate change. This is one of the events where we actually don't know yet whether or not climate change played a role in that. And I'll explain a bit about why and hopefully show you that we actually could answer the question, we just haven't done it yet. So there has been extreme weather events have happened always, and we don't know much about it really, because in most places of the world, we only have reliable observational records since the satellite area began. And in some places, we have longer records. And the longest record we have for precipitation in the world is actually in Oxford, and it started in 1766, which is, compared to how long we have weather out there, not a very long record. And in most other places of the world, the record started in the 1950s or over land 1900. And then, over the oceans, we really only know it a lot since the satellite area began. And it's still, in a lot of places, it's still problematic to get reliable observations even today. So, taking this into account, we will never be able to say with certainty that a certain event would not have happened without anthropogenic climate change, because we can't know that. There is always a lot of internal climate variability, and all events have more than one cause. So we will never be able to say that with certainty. And even if in the last winter in Oxford the record was broken of precipitation, so it was the highest precipitation ever recorded in that area. But when you look at the flooding, it is actually, well, hardly on the scale. So there's also extreme events are mostly realized by people through their impacts, but that is not the same as the extreme weather event. So there was more precipitation or more rainfall than there has ever been before in Oxford, but there was hardly any flooding. And there were huge floods. For example, up there is a flood that was in 1897, where compared to the record, it did not rain that much. So that shows weather events and then extreme weather events and their impacts are always very complex, and we will not be able to say for certain that a certain combination could not have happened without anthropogenic climate change. However, what we can say instead is we can ask the question, how has the risk of a certain event occurring changed due to anthropogenic climate change or due to other factors? So you could imagine if you roll a dice, and on average you roll a 6 every 6 times. Well, when you roll the dice 10 times and you have 5 6s, then you think, oh, I'm really lucky or unlucky, depending on what game you're playing. but you would not think that there is something wrong with the dice, because from only rolling it 10 times, you will not be able to actually say something about the statistics of this event. And this is sort of the same problem that we have when we look at extreme weather events just in the observations, that we only have very few of them, and if there is a certain number of really extreme events, we might suspect that there is something dodgy or some probabilities of a certain type of event occurring have changed, but we don't know that from just looking at the records. So what you need to do in order to be able to find out whether or not you actually do get too many sixes on your dice and whether your die is loaded, you need to roll it again and again and again so that you are truly able to investigate the statistics of it, and then you may be able to find out, oh, actually, I do get a 6 on average, two sixths of the time and not 1/6. So then you know, okay, our die is loaded. And this is what we can also do for the weather, which is where we can use climate models for. And this is what we, for example, do Peter Stott is doing that in his group, and we are doing that in climateprediction.net, that we do exactly the same thing. We simulate the weather over and over again under the exact same climate conditions, and with this, we get the statistics of possible weather. So, for example, there is an extreme precipitation in Oxford last winter. So what we do is we run the climate model with the observed greenhouse gas forcing that is in the atmosphere, with all the observed natural forcings that will drive our model. But then the atmosphere in our model is free to do whatever is possible as a weather event under these constraints that we have. So we get some extreme weather winters, some extreme low precipitation winters, maybe, if this is possible under the given climate conditions, and a lot of very average winters. And then we can count how often do we actually exceed the threshold that we are interested in, that we have used to define the extreme event, where we want to know, has this extreme event actually changed? But of course, when you roll a die, you know that a 6 has a probability of 1 in 6 if it's not loaded. But for the climate system, you don't know what the counterfactual experiment would look like. So what is the world without anthropogenic climate change? We don't have observations of that world. So you need to model that as well. And this is then your normal dice that you have a model where you do not use the observed climate conditions in the atmosphere and the observed greenhouse gas forcing that is there, but you use the pre-industrial concentration of greenhouse gases in the atmosphere and then do exactly the same experiment. And with this, you are able to have 2 sets of statistics of extreme events, and you can compare them. Oh, and this is the wrong figure. Okay. What you have when you've done that is that you have 2 sets of statistics of extreme weather events, and this is what you see here. Although it is not normally, you would probably draw it as a distribution, so just a PDF of where you count the weather events in the world with climate change and in the world without climate change. And then if anthropogenic climate change, so the greenhouse gases in the atmosphere in this way of doing it, have changed the risk of a specific extreme event occurring, then these probability distributions, or this curves that show how often a certain type of event occur, would not be on top of each other, but would be shifted, so that you see one event occurring more often in the world without climate change, for example. And the same is what you can see here on this plot. So this blue curve here is all our simulations of possible weather in the world with climate change, so in the world we live in, and each blue dot on this curve is one simulation of possible weather. So each blue dot is one possible winter of the year 2014. And we have sorted them by their occurrence probability. So the lowest, the winters, the thresholds that you exceed most often are down here in the bottom, and the thresholds that you exceed hardly ever, or 1 in 100 years, are up there. And the green curve here is the world that might have been. So our attempt on simulating the world that might have been, the winters in the world without climate change. And you can see, and the other green curves are other attempts, because we have no observations of the world without climate change. We have fewer constraints on how that world looked like. So our model simulations have a larger spread. So this is the uncertainty around it. And you can see that the curves do not really overlap, but they are pretty close. And the uncertainty is actually around, so there is quite a lot of uncertainty around it. So there is a signal, but it is rather subtle. So in this case, we could say, okay, climate change has made this kind of extreme precipitation in southern UK a little bit more likely by 25% in this case. But it's a signal, but it's not a very strong one. And here you can, so this is when you zoom out of it. So this is just the events between 1 in 10 years and 1 in 100 years. And here you see actually this is the sort of precipitation that you have every year. So this is the normal event, the average events. And these are the events that are really, really rare, which we have never observed, and we might never observe, because this end of the curve, it's really hard to say much. But here our curves look quite straight, and we actually have a good idea of that this is a good signal. So this is how we can do that. And for example, the figure I wanted to show, but which was wrong, was about the Australian heat wave in 2013. And there you have a very strong signal, so that in your model world, you could actually say, without anthropogenic climate change, you would not have been able to get this kind of event. But this is obviously a model world, so there are uncertainties around it because our models are not perfect. But you can get very strong signals, and you can make very strong statements how anthropogenic climate change has influenced the world we live in and the extreme events. But this is not the case for all extreme events. So this one is a much more subtle signal, and there are also extreme events which have been made less likely due to anthropogenic climate change. And there are quite a few ones, for example, Hurricane Sandy, where no matter how you approach it, you cannot see that climate change has altered the probability of such a storm occurring. What is really crucial to be able, or when you communicate the results of these kind of attribution studies, is what is an event. Because for most people, the important thing about an extreme weather event is the impact of that. So a failing harvest, or the destruction of yield, or impacts which follow from the meteorological event, but are also confounded by other factors and not just the meteorological event. And then you could, the most straightforward way to define your event and to do attribution studies is just looking at precipitation or temperature or whatever meteorological variable you have exceeding a threshold. So here in this case, there is, for example, you draw your threshold somewhere here and then count, okay, there's 1, 2, 3 of these extreme events, and than you do the world without, and you maybe have just 5 or so. But you would like to do some larger ensembles to have more like 100 in this world and 500 in the other world, so that you have a robust signal. But then, of course, not all precipitation, or not all rainfall in the world, and not all storms, for example, are the same events, because some of them come from one particular atmospheric circulation state, and one come from a very different. And you might also want to ask, has not just the variable you can directly observe, like rainfall, changed, but has the state of the atmosphere, or the predisposition of the atmosphere to be in a certain state to allow for a certain type of extreme event to occur, has that changed? In which case you might want to define your extreme event a bit different. And this seems a very academic discussion, but obviously it matters quite a lot. And here we have again these return time curves, and the only thing that you need to understand about them is if they are separated, then there is a signal, and if the red is the world with climate change and the blue one is the world without climate change, and if the red is above the blue, then climate change has increased the probability and the risk of this kind of event occurring. So when you look, for example, there was a heat wave in Serbia in 2012, and when you just look at temperature, you can see, okay, the event here is from a 1 in 10 year event, is a 1 in 10 year event in the world we live in, so with climate change, but it's almost only a 1 in 100 year event in the world without climate change. However, when you not look at temperature, but look at heat stress, which is a combination of temperature and relative humidity, which is actually what matters when you think about mortality rates, which is what the human body responds to rather than the absolute heat, then you see that that there is still a little signal, but it's much more subtle. So you need to be clear what is the question you ask, and you need to communicate what question you answer when you do this kind of study. So there are quite a lot of challenges with this method. For example, we can't say much about hurricanes yet because we don't have the modeling capability to run large ensembles with hurricanes. We can say something from our general understanding about them, but we can't really do the studies in the same way that we can do with temperature or with extreme precipitation. So there is a limit to the kind of extreme events we can look at. Then, of course, it is important how you communicate that, and that is not always easy. So a lot of people don't really like return time curves. So this is clearly a challenge if you want to use this to inform policy. You need to make sure that you communicate the right thing and what you actually communicate. And then how does it relate to the impacts of the event, and not, so if you don't, just looking at the meteorological variable, it might not be the most useful thing. However, when we actually do that, and when we would do that in a more, at the moment there are a few attribution studies about some extreme events that interest researchers because, well, they live in Oxford, or because there are quite a lot of studies on the Australian heat wave because there's a lot of climate research going on in Australia. But there is hardly any attribution research going on in developing countries, and so there are huge gaps at the moment. But if we would do that more systematically and more comprehensive, then we could get a lot of understanding of how actually anthropogenic climate change is affecting us now, which is as such great, but it would also then, of course, help to forecast these kind of extreme events in the short term, and would help to better react to this kind of extreme weather events. Another aspect is we could actually work out how much climate change is costing us today, because you could not just go through the impacts, you could actually look at the costs of that and have a better idea of how much it actually costs us than the assessments we are doing today. And it would enable us to actually put things like the loss and damage agenda, which is currently one of the pillars of the UNFCCC climate change negotiations, where they have the mitigation and adaptation, and then loss and damage dealing with residual losses and damage that you cannot adapt for and cannot mitigate, if we had an idea of which of these extreme events are actually due to anthropogenic climate change and which are not. And yeah, Peter will now talk about a bit more about how we go about as a scientific community to make that a bit more systematically. Thank you.